Hello, everyone. So maybe it's time to start the next talk. So, so the speaker is Professor Lapid from Weizmann Institute of Technology, and his title is Eisenstein series. So let's welcome.
Okay, thank you very much for the introduction, and of course to the prize committee and for the organizers for this beautifully organized conference, and of course all the staff involved in this, and the students, volunteers, etc. So what I will speak about. Yeah, so this is the joint paper with Joseph Bernstein that appeared only this year technically, but in fact this work should have been done many years ago. They will explain. So what is the history briefly? So Eisenstein series, they go long way back, but the modern theory started with mass, who is also known from mass form. So in the same paper, he introduced the Eisenstein series as we see in the modern perspective, and Selberg understood the relevance to spectral theory, and this was fully generalized by Langlands in his famous work on spectral theory for automorphic quotients. And the point of this paper is to give a simple proof of the meromorphic continuation of the Eisenstein series, which is a key in this program. And it's based on an idea of Bernstein, which goes back to the 80s. So Professor Bernstein, unfortunately, was not able to come, but he will make do with me. So what are the Eisenstein series? So, and I hope at least the talk will be reasonably understandable. There are no derived categories or anything. So the Eisenstein series, which Eisenstein defined, well, first are the modular forms, Eisenstein series, which are, I assume that they're known to most of you. They are given by this series over lattice points, functional lattice points. And this is a modular form. So I guess the lighter doesn't work, but okay, this should be familiar to you. And it's a modular form on the upper half plane. It satisfies the formational equation under SL2Z acting by Möbius transformations. It's of weight 2k, so k is the parameter here. Well, it converges for k bigger than 1. But the types of Eisenstein series that I will consider are not quite like that. It's some variant of this, which was introduced by Mass, as I said, back in the. So Eisenstein was born a little bit over 200 years ago, and now we were doing some fast forward to Mass, but this was still close to 100 years ago. Anyway, so introduce this Eisenstein series. So the difference is that, okay, there is y to the s plus half in the numerator, but instead of, so I want to kind of do interpolation in k, but I put absolute value. So it's no longer holomorphic in Z, it's just real analytic in Z, but now you have this continuous parameter S, which I take to be a complex number, and this will be analytic wherever it converges for real S bigger than 1/2. In this normalization, this is convenient normalization. And it is certainly the way that it is written, well, it's easy to check that this is actually SL2Z invariant rather than, satisfying some more complicated transformational property. It's actually invariant under gamma. Yes, and I recall the SL2R. So unfortunately, I'm not sure, but it's all visible here, but I mean, SL2R, of course, acts by Möbius transformation. If there are any questions, please don't hesitate to stop me. Sure. Everything with me? Yeah. Fine. So what is the point now? Yeah, so I said that, so there are two parameters, Z and S. So S is the spectral parameter. It's a priori in some real half plane. and Z is in the upper half plane, but it's really H mod gamma. So the familiar picture. This is a fundamental domain for, H mod SL2Z. So that's where the variable Z really lives. And yeah, so now we can analytically continue this function as a function of S using the Poisson summation formula. This is basically the same as what Riemann did 100 years before mass, for the Riemann zeta function. So it's basically the same proof. And you see that the Eisenstein series has a pole at S equals 1/2, corresponding to the pole of the Riemann zeta function at S equals 1. And it has a functional equation, again, which is reminiscent of the Riemann zeta function. You have to multiply by some gamma factor, some pi to the minus S, and then you have the functional equation relating S to the minus S. So here it's more convenient to normalize it this way. There's always the shifts. So S goes to minus S, unlike the Riemann zeta function, S goes to 1 minus S. Okay. And the residue at S equals 1/2 is actually a constant function, constant in Z, which you can compute. Not so important what it is, but so far so good. Okay, now notice that I put a star on the Eisenstein series. So the reason is that there are kind of two variants of this Eisenstein series. I mean, apart from the modular form, we forgot about the modular form. Now we are talking about this series, which is holomorphic in S. But the point is that you can either sum over all lattice points except the identity, except the origin rather, or you can just sum over the primitive lattice points, those with GCD 1. The difference is small because you can just easily see that one is proportional to the other by factor zeta to S plus 1. You just pull out the GCD. But the difference is important, and somehow it's more natural for some, in some respects, it's more natural to consider this Eisenstein series without the star, so only some of the primitive lattice points. The reason, one of the reasons is that you can actually write it as a sum over coset. So what are the primitive lattice points? You can think of it as a quotient of gamma SL2Z mod gamma infinity. This is the elements of SL2Z with ones on the diagonal and 0 below. I mean, the point that this gamma infinity preserves the last row. If you multiply on the left, it preserves the last row. So the last row of the matrix in SL2Z is a primitive vector, and gamma mod gamma infinity just tells you that that's what remains, so to speak, from gamma after you mod out by gamma infinity. So this is just a simple observation. And so it's kind of more natural, it's naturally gamma invariant because I sum over the coset. And so again, of course, the functional equation is inherited to this Eisenstein series, and it boils down to what I wrote here. So instead of, so you just have to do the arithmetic, and that's what you get. You get zeta 2s over z2s plus 1 in the is the proportionality constant, and of course, times the Archimedean factor, which is just a beta function. But the point is that, as I said, this Eisenstein series is kind of the more, in some sense, natural object in some respects. Now, I said that the Eisenstein series is a function on the upper half plane, which is invariant under gamma. It satisfies some properties. So first of all, you have the Laplace-Beltrami operator on the upper half plane. This is an invariant operator under the isometries, so SL2R acts by isometries. And in fact, it generates the ring of invariant differential operators. And so in particular, it descends to any quotient like H mod gamma. And the Eisenstein series are eigenfunctions. The reason that they are eigenfunctions simply is that the function y to the s is an eigenfunction, and then you just average, so you see eigenfunction, but now you're also invariant. So these are eigenfunctions on delta, which are gamma invariant. And now they're never in L2, so H mod gamma is not compact. It has this cusp. Yeah, I should say, of course, that the metric here is not the x square plus dy square, the x square plus dy square over y square. So that's why this is really a cusp. So the circle here is length 1 over y. Well, this is the height. Z is equal to x plus y. So it's not compact, but it's finite volume. And so anyway, so these Eisenstein series are never L2, but they want to be L2 when real S is equal to 0. Of course, this only makes sense after you morphologically continued. And in fact, they furnish the continuous spectrum of delta. So what that means formally is that for any function in L2, you can spectrally expand. So you have this orthogonal basis of actually bona fide eigenfunctions in L2, which you treat as black box. Of course, they are very deep, and it's very hard to write something down, except of course for the constant function. And then you have this this integral. You integrate against an Eisenstein series. So that's simply what means that the Eisenstein series gives you the continuous spectrum. Any questions at this stage? Okay, so let's move on. So as I said, so if we specialize to the case of SL2, our paper is more general, but in the case of SL2, the paper gives a different proof of the meromorphic continuation, and therefore of the zeta function, because as I told you, there's a close relation between the Eisenstein series and the zeta function, by a method which is not based on the Poisson summation formula. So for SL2, you can do kind of many things, but the point is that this generalizes. As I said, it should really have been done before, but there's a long history for Eisenstein series, and the level of documentation has been a bit substandard, one could say. But anyways, that's where we are. And I should say that when you go to high rank, I won't have time to say much about this, but the Poisson summation formula is not applicable if you try to do the general theory of Eisenstein series. At least we don't know how to make it work. Okay, so let me explain briefly. So I wrote something about the history. Good. So as I said, Selberg considered it. He understood the role of Eisenstein series for spectral theory. He developed the theory mostly for rank 1. He developed the trace formula. And Langlands undertook the theory of Eisenstein series for arbitrary locally symmetric spaces. This means that G mod K mod gamma, where G is a simple group, in case it's maximal compact. And he obtained in his famous work in the 60s a spectral decomposition of L2 G mod gamma in terms of Eisenstein series. And of course, discrete spectrum of lower Levy subgroups. And his work is a tour de force, and it took him some time to publish it. Finally, he published something in the 70s, and then it took some time for the community to digest it, and it resulted by a textbook by Muglen and Wolfsberger, which roughly follows, it interprets Langlands. So it's like Confucius, and it has interpreters, and somehow they give you some theory at the end. So it takes time to digest. And now, as I said, in the 1980s, so before anyone here was born, surely, Joseph Bernstein came up with then a new idea, simple idea to meromorphically continue the Eisenstein series. This idea is based on the principle of meromorphic continuation, which is an elementary idea which I will explain next. And the main feature of this approach, I won't have time to explain it in detail, but the point is that, so spectral theory is of course the major application of Eisenstein series, but some of the meromorphic continuation itself should be considered separately of spectral theory. I think that's really the main insight of Bernstein. Once you realize this, then somehow, in mathematics, things are usually psychological barriers. So once you understand this, then easier to proceed. Okay, so I will illustrate it in the simple case of SL2. So, but now let's go back a little bit and forget about everything I said before and just consider a very simple situation as follows. So I consider nothing more than a system of linear equations in a vector space, in a complex vector space V. Let's call this system Xi. And this system is just given by, a linear operator applied to V is equal to some vector Wi. So you have I just some index set. It's infinite in general. And for every I, you have a linear operator from V to some space Wi. And you have this equation AI of V is equal to Wi. So think of AI and Wi as just constant operator and vector, respectively, and you want to solve in V. Okay, so you get some different space solutions. And of course, these are how linear systems appear naturally, but you can always assume without loss of generality that it's not a linear operator, but actually linear functional. Just apply enough linear functionals and it's the same system. So I'll write it as, there's no marker. So mu iv is equal to ci. Now ci are constants, scalars, and mu I are linear functions. Okay, but in reality, the V is not just a vector space, it has topology, so it's a Hausdorff locally convex topological vector space. Just think of your kind of favorite topological vector spaces, and the mu I are continuous. That's one thing. More importantly, you have now not one system, but a family of systems which depends holomorphically on a parameter S. Let's say just a complex variable. It could be, of course, in a complex manifold, it doesn't matter. So you have this family Xi S, and what it means simply is that so I want to say that it's analytic, so the I, the index set is just fixed, but the mu I and Ci depends on S, they depend holomorphically. So for Ci just means that this is a holomorphic function in S. For the mu I, since it takes values in the dual space, well, it just means that if it's holomorphic in the weak sense, in other words, when you apply to any vector, you get scalar analytic function. So it's a very kind of basic notion of holomorphicity. So this is just terminology, if you like, and then the principle of meromorphic continuation says the following. So suppose you're given such an analytic family of systems of linear equations. So the coefficients, so think of mu I as the coefficients, also the Ci, that's the free coefficients. They depend holomorphically on a parameter, but it's kind of infinite dimensional topological vector space. So what do we assume? We give ourselves two assumptions. One is kind of technical, but you have to give yourself some kind of assumption. This is the local finiteness. It means that around any parameter S0, you can put the space of solutions of Xi S, which is some affine space. So first of all, I'm saying that it's in fact finite dimensional, but moreover that it's a priori contained in some image of analytic family of, in fact, injective is not too critical, but let's put it from some fixed finite dimensional vector space L. So a priori, the solution space is inside some vector space, kind of finite dimensional family of finite dimensional vector spaces which vary analytically. So this is some technical condition, which of course is a non-trivial assumption. And then the more fundamental assumption is that this uniqueness assumption, so that there is the set where this system Xi S has a unique solution, let's call it Vs, has a non-empty interior, just in the usual topology of C. So these are the assumptions. And then the conclusion is that, first of all, so that this Vs, which a priori lives in some set S, which I'm not even saying that it's open, but eventually S is open. And in fact, S is the complement of a discrete set. And Vs is meromorphic on C and analytic on this uniqueness set S. So in other words, you can multiply it by an entire function, a scalar entire function f, which is non-vanishing on S, such that fs times vs is entire. So that means that you apply any functional, it will be entire. Okay, so a priori you start with some uniqueness set, which is like the right half plane for that matter, but then you get for free that you have meromorphic continuation. So that's the principle of meromorphic continuation, which is in fact, in some sense, easier to prove than to state, but that's really a wonderful statement. But of course, it's only as useful as what you can do with it. So it takes a little to digest, maybe the first time you see it, but I hope it's simple enough. Yeah, sure. Yeah. So a priori, you don't know. I mean, it could be that at some singular point you will have more than one solution, but the theorem tells you that in fact it will be a discrete set, or it's a bad set. So the uniqueness set will be, a posteriori, it will be a complement of a discrete set. So the proof is very simple. So it's basically some Cramer's rule, nothing more than that. It's just that the concept is useful. But how would you use this kind of principle? Well, the main technical difficulty is to check this local finiteness, and local finiteness is given by, so there is a simple criterion to check local finiteness. It's called Fredholm's criterion. It's based on, I don't know when was Fredholm, maybe late 19th century, early 20th century. It's very basic. So what it says is that if you have, so suppose I have some equation which is given by some operator of V. This is a homogeneous equation, but it doesn't matter. So some operator mu s is given by some operator mu s, and now the mu s, I assume that it's compact. Let's say mu s naught is compact, and the nu s naught is a strict embedding. So that means that it's injective and the image is closed. So think of just compact operator. So just compact operator of V applied to V equals V, right? That's kind of the basic example. So we know by Fredholm's theory that this space is finite dimensional. And this is just an elaboration of this fact which tells you that, the proof of that in fact gives you that it's locally finite in the sense that I described before. And how do you check that an operator is compact if you want to apply this? Well, if you have Hilbert space, then usually you check that an operator is Hilbert-Schmidt by giving some estimate. So if you have an operator from a Hilbert space to L2 of some measure space, and it's given by, the point evaluation is given by some continuous functional, and the norm of these functionals are in L2, then this is a Hilbert-Schmidt operator in particular compact. And it's more or less if and only if. So in practice, you need to give some estimate, right? But this is how you do it. Okay, so how do we apply it to our case? Well, in our case, we have to explain some things about the case and about the quotient H mod gamma. Well, so only thing you need to know that you have some compact part, let's say up to here, and then you have this cusp. And the nature of the cusp geometrically is very simple. So this is what's called the Ziegler set. So this is just everything above this, or actually above here. So it contains a fundamental domain. And now there is a notion of functions of uniform moderate growth. So I don't want to get too much technical, but it just means that the function is bounded by some power of y. So again, y is bounded below, so power, but the power can be any. So it's a fixed power, but it's not just for the phi itself, but also when you apply any number of iterations of the Laplace operator. So it's important that n is independent of k. Of course, the constant can depend on k. So this is the space you're going to work with. The Eisenstein series will be there. And another important concept is that of a constant term. So given a function on h mod gamma, you construct a function in y, which is just integrating, averaging along these lines with a fixed y. So the function is already a function on R mod z because of the invariance under gamma, and I just average. It's a compact set. It's a circle. And the point is that for any function in this space, the function is well approximated by its constant term. So the difference is bounded by any negative power of y. It's rapidly decreasing. That's because the nature of the geometry that we have discussed. These are very elementary states. So in particular, the growth is determined by the constant term. And then we have this notion of Cas forms that mean that the constant term is identically zero. So the constant term is a function just on the positive real line. So these are some aspects that are kind of basic here. And now let's go to the proof. So okay, recall, so we have this Eisenstein series. It's a function on h mod gamma. It is a function of moderate growth, uniform moderate growth. That's just some kind of checking whenever it's convergent. Now, what are the system of equations that we are going to use? The principle of powerful continuation. Well, so remember that it was an eigenfunction under the Laplace operator, but now I will change it. This is a differential equation. I will change it to an integral equation for technical reasons. The integral equation means that when I do a certain convolution that I will not describe, this Eisenstein series, which I call it psi, is an eigenfunction under the convolution operator. So this is basically equivalent to the being an eigenvalue of the Laplace. That's one set of equations. So this is true for any test function on the real line. And h hat is just the Fourier transform, the usual Fourier transform. Actually, it's for every even test function, if it matters. The other important equation is about the constant term. So this is some computation. When you compute the constant term of Eisenstein series, well, there is a contribution just from m equals 1, n equals 0. So this is just y to the s plus half with this normalization. So that stays put. But then there is another contribution, which is more complicated, coming from the rest of the term. But what you see is that the exponent of y is minus s plus half. Now, it's very important what is this question mark, what is the proportionality constant, because that's actually going to be like quotient of zeta function. So it's very non-elementary. But the whole point of the proof that you don't need to know what it is. It's just a black box. Because knowing the morphic continuation of this question mark is equivalent to knowing that of the Eisenstein series. So we go in circles. But for the proof, you don't need to know anything. You only need to know that the main term is coefficient 1, which is elementary. So the way to write it formally, this is the way, simply that if you remove the y to the s plus half, then you have eigenvalue minus s plus half, so you have this equation. I just wanted to show you that this is a bona fide linear equation. You can write it this way. And the final equation is that it's orthogonal to Caspidal function. That comes just from the fact that you average. This averaging is kind of dual to taking constant terms. So this is elementary. So these are the three sets of equations. And the claim is that these give you the system of linear equations for which you can apply the principle of meromorphic continuation. The space V, yeah, so sorry. So the space V was the space of smooth functions of uniform moderate growth. And the vector that they want to solve is, the system is on now what I call psi. So the claim is that first, the Eisenstein series satisfies this, so this is some computation. And secondly, that you have the local finiteness and uniqueness. will guarantee, so the uniqueness for real is bigger than 1/2. This will guarantee that you can use the principle of homomorphic computation. Okay, so what is our job now? So, okay, I just rewrote the system. So the claim is that every talk should give you just at least one proof, right? So this is the proof. So the claim is that I will show you uniqueness. And in fact, the last two equations already give uniqueness for reals bigger than 1/2. So what does it mean? It means that, okay, I already know that I have one solution, the Eisenstein series, but any other solution, I mean, there's no other solution, right? So if I consider the difference of two solutions, I want to show them 0. But what is the difference of two solutions? So I kill the non-homogeneous part. So that means that the constant term is now proportional to the y to the minus s plus half. But because real s is bigger than half, this means, so this decays, right, for y bigger than bounded away from 0, this decays. So in regular, it is bounded, but I told you that every nice function, every function v is controlled by the constant term. So if the constant term is bounded, the function is bounded. But now the function is bounded, and now the function is also gamma invariant. So this contains a fundamental domain. So this now is bounded on all of H. So in chess, you would put like an exclamation mark, right? Because this is kind of the key step. The function is bounded on the fundamental domain, so it's bounded on the whole space. And now if the function is bounded on the whole upper half plane, then the constant term is bounded, right? Because it's just taking average of the value. So it's also bounded, but now it's bounded for all y bigger than 0, not just for y bigger than 1/2, but for all positive y. But again, the constant term was y to the minus s plus half, but now you go to 0. So this function cannot be bounded as y goes to 0 because real s is bigger than half. So therefore, this star must be 0. This means that the constant term is 0, and therefore it's a cusp form, so it cannot be orthogonal to cusp. So this is kind of a very nice argument to digest, but this is all what it is, what it takes for the uniqueness, which is, as I said, the key feature. And of course, you also need to say something about local finiteness. So in other words, I will not want to spend time. It has been a long day. There's also a long evening for some of us. And I did a mistake because on Sunday night I woke up to watch the Euro finals. Then to make things worse, I forgot to set the alarm of the next day. So also today I woke up at 3 a.m. My stupidity. Anyways, so let me not go into that. I'll just say that basically what goes into the local finiteness is, well, so you have some integral operator, as I said, but the point that it's not compact because H mod gamma is not compact. So you have to split somehow the set. You have to treat separately the cusp and the compact part. Compact part, the operator is compact, so to speak, but the cusp you have to say it a little differently. But the upshot is that the first two equations now. So I said that the uniqueness is given by you just need the last two equations. For the local finiteness, you need the first two equations. So the first equation is not enough because delta H is not compact, but together with the second equation, it gives you some nice compact operator, for which you use the Vertron theorem, and I will leave it at that. Now, let me just finish with saying that so just a few remarks. So first of all, so the proof, I used gamma is equal to SL2Z. I used the very explicit Eisenstein, but the proof is robust. You don't need to know that it's a uniform, that it's an arithmetic lattice. It works for any non-uniform lattice. Of course, if it's a uniform lattice, then you don't have Eisenstein series. Eisenstein series come from the cusp. So arithmeticity is never used. And of course, okay, so it also works for function fields. These are kind of, if you like, discrete analogs of H mod gamma. And the Eisenstein series are actually much simpler. Analytically, they are just rational functions in this case, in the spectral parameter, or the relevant spectral parameter, I should say. And in that case, the proof is in fact simpler. You don't need the local finiteness, which is kind of the analytically difficult part. And also, you get the functional equation. The functional equation comes from uniqueness. But I will not say more than that. Just final words about the general case. So this was kind of a baby case for SL2. One can write nice formulas. In general case, one starts with a reductive group, like we had last talk, those who were here, and one considers quotients by lattices, but in high rank, lattices are automatically arithmetic, but it doesn't matter, as I said. And okay, for the general theory, one starts with some automorphic form, whatever that means on the Levy part. So you have this, the cusps are more complicated, but somehow they are dictated by certain parabolic subgroups, which have to do with the gamma. I mean, they are kind of compatible with the gamma in some sense, and you consider automorphic form by kind of averaging, like the Poincare series that we heard in more fancy language in the last talk, some variant of that. Anyway, so again, this series converges. Now you have multi-parameter. It converges in some right-half plane, and you concoct from this Eisenstein series, which then you want to homomorphically continue, and Langland's theory tells you that the spectral decomposition is given in terms of this Eisenstein series induced from the discrete spectrum of the Levy. Okay, so our paper gives a simpler proof of the homomorphic continuation of Eisenstein series based on the same ideas. There is some more bookkeeping, obviously, but the lion's shares of the ideas are already for SL2. And of course, it uses fundamental aspects of automorphic forms, which go deep into the last millennium. Gelfand, Shapiro, Harishchandra, Langlands, etc., but it avoids the more complicated arguments of Langlands, etc. And I should also say that the Lom subsequently gave a simplification of the proof of the spectral decomposition, the highlight of Langland's theory. It's based on his earlier work, on some work of mine. But anyways, this is now available. Anything more I want to say? Yeah, so of course Eisenstein series play a ubiquitous role in the theory of automorphic forms because many questions you need to attack, or it's natural to attack them through spectral theory. So anytime you have serious applications of spectral theory, you need to use Eisenstein series. And of course there are gazillions of works like that. And Eisenstein series are important for other aspects. So for instance, constant term computation that I hinted in the SL2 case. So if you remember, there was this zeta function, or quotients of zeta function. So this persists for general Eisenstein series, and that's Langland's fundamental computation from the 60s, which led him to the general concept of automorphic L function. So it cannot be underestimated. And the notion of L group, which is kind of embedded in the definition. So it's really very, it's one of the fundamental computations, automorphic forms in the last millennium, last century, millennium, whatever. And that led him, of course, to the functionality conjecture, etc. But it's not only that the constant term of the Eisenstein series are important. You can consider the entire Fourier expansion, and that's, of course, what was done early on in the theory. And these are, there's valuable information there, which, of course, I don't have time more than just to say two words, but these non-degenerate critical Fourier coefficients, that was also a theme which was very important last century. Langland's Shahidi method, those who are aware of it, major successes. And there are more elaborate Fourier coefficients of Eisenstein series, which give powerful constructions, which, in fact, it was realized relatively recently by Ginsburg and Sudry that the whole of packets in Arthur sense can be realized in terms of Fourier coefficients of Eisenstein series. It's quite remarkable. And Eisenstein series are also good precursors to understand conjectures about periods of automorphic forms because it's much easier to compute periods of Eisenstein series. And they're important in their own right beyond predicting what happens for Casper. Okay, so I think I will end here. Thank you very much.
Any questions?
Yes.
Any questions? So this proof for SL2 generalizes to the other cases? Same lines.
Sorry?
So this proof for SL2, right?
Yeah. So, of course, when you work with high rank groups, there is more combinatorics. There is not just one parabolic, there are many parabolics, but finitely many. So you have to build it in a more robust way. I mean, the most technical part is the local finiteness. The uniqueness works more or less the same, but you can kind of reduce to this.
For example, what is the replacement for the second condition, this constant term of this form?
Right. So you have to consider what is called the cuspidal components. So in general, the constant term, here it's just y to the s, some exponential. In general, it will be an automorphic form. So it has a cuspidal part, so to speak, cuspidal projection. And what you want to say is that the cuspidal part of it is basically the cuspidal part of what you start with, plus something else, which you kind of don't care about, except you care only about the exponents. The exponents, you have some Weil shift. That's why you can kind of make everything else kind of negligible in some sense. Of course, you have to work it out precisely. It's a little delicate, but it's in the paper. And the local finiteness is even, so again, you have to kind of split the things to parabolic subgroup, and you get some Fredholm operator, compact operator in each parabolic subgroup separately. So it's more elaborate, but in terms of ideas, I think the ideas are already necessary. As usual, you have to work out, and that's why it took some time to, to go from an idea to implementation takes some time. But though if Eisenstein series, I think it's the time it took was too long. Okay, that's where we are. The functional equation is it's a direct consequence. So you have an intertwining operator. It's not a scalar. You have an intertwining operator, so it's operator valued, but it comes. The proof gives it, right? Because once you have uniqueness, it means that if you go from S to minus S, they must be proportional. As long as you don't know what is as long as you don't care what is the proportionality constant, the functional equation is formality. To get the constant, it's exactly what, the question mark is exactly the proportionality constant. So you just have to realize that the question mark is the intertwining operator, but that's kind of not difficult. But the short answer is that it's a consequence of the uniqueness principle as well. I don't know if it's a good answer, but that's a short answer. More questions?
So this condition where you write down equation satisfied by function psi, I mean,
Which equation?
this one where it
This
is,
one?
Yeah.
Yeah.
So is it kind of you replace Laplace operator with this?
Okay, so the first equation actually is a replacement for the Laplace
The first
eigenvalue.
one.
But you're right, of course, that the constant term also inherits the equation. So the fact that you have s and minus s, that comes from the Laplace equation as well. The point is that this is the only non-homogeneous equation, right? In all this, so you need a non-homogeneous because otherwise, if you had uniqueness, the solution will be zero, right? But so this is the only non-homogeneous equation, and the point that you have coefficient 1 here, that's the key. The fact that it's it's a linear combination of y to the s and y to the minus s is clear from the Laplace equation, but what I insist here that the equation really says that the coefficient is 1. So this actually gives kind of an alternative definition, if you like, or characterization of Eisenstein series. Instead of writing some complicated series, you say the Eisenstein series is the one which satisfies.
Yes, and you are able to do it in general case.
Right. So the general case, the formulation, of course, is a bit more involved because I have to, because of the many parabolic subgroups, I need to say exactly what I mean that the constant term is of this form. So there are some projections, kind of Caspian projections. Okay, but this again, so Harishchandra did some decomposition into Caspidal parts of each parabolic. These are well.
Yes, so this is Harishchandra.
So yeah, so we use, of course, a lot of like in the book of Harishchandra, in the 70s, I don't know, early 80s. I mean, he died in 83, so he couldn't be much later. Could be later than that. But anyways, he explains the basics of the orthomorphic forms, and of course, this part is the building blocks. So that's kind of used. But these are kind of soft arguments and concepts.
Thank you very much.
There's no spectral theory involved. Deep spectral theory.
Any other questions? Okay, if that's not the case, let's thank Professor Lapid.